using the notes as my lecture for today, and we will just go through what we have discussed last time, this time using the lecture notes. So we will review the Wishart distribution. That is, we start with section 17.3, and last time we ended at 17.4, and we will start at 17.5 later. So I will just go through this note of what should be remembered in this section. So we will start in section 17.3. This is actually 17.3. This is the so for the assumptions before we can get to a random matrix to be a Wishart distribution. First, we have a random matrix here. Take note that this is not a univariate case, but this time this is a vector, no? Because X here is an n by p random matrix, so you will expect this to be a 1 by p vector, and this one is also a 1 by p. So together it's n by p, and this random matrix should satisfy this distribution, a normal distribution with a mean mu psi. If this time the covariances that deals with the rows or the xi's here, I from 1 to n, is just the identity matrix, and this sigma here is the covariances between columns. Okay, so the xi primes here are still normal with mu I prime, and it has variances among the columns or among themselves, no? So also let wx prime x, which is the summation of x prime I xi. So this is how we transform the random matrix X to a W, which will become a Wishart distributed random matrix, which is in a quadratic form. Now, note that W here is now a P by P matrix, and in general, it's a non-negative definite matrix. So here, if that is the transformation, we have a W which is a Wishart distributed random matrix, or it is said to have a Wishart distribution. Okay, so for theorem 17.5, it tells you that the W here only depends on your mean vector mu from here, which is since it is x prime x, so it becomes mu prime mu. Later, this mu prime mu will be denoted by delta. So to prove that, which we skipped last time, so it has to go through some subsets of information. First, it's going to use the concept of orthogonal matrix, and then you do some transformation here. So just read through that, and then you will have a distribution of that transformation, which is they are equal in distribution to this distribution here, W and mu. And then it will try to look at this mu prime mu and see if it is an invariant with this group of transformation. So when we are talking about invariance, it has a corresponding group of transformation, and in particular, it is a maximal invariant estimate. So later, if we extend chi-square, the ratio of chi-square which becomes an F statistic or an F distributed random matrix, we see also because of this property that the F stat is also an invariant test. No, so you have to go through that using the orthogonal concepts and the invariant concept, and then use some theorem in appendix to conclude that mu prime mu is a maximal invariant. And then after doing that, you have a function f here of w, and some transformation will be equal to this. It's just the same to this distribution here. They are equal in distribution. And then see that w just depends on mu through mu prime mu. So after doing that, so we know that w is will be dependent on mu prime mu, which later will be denoted by delta, and we write this notation. So if we have an x transformed as x prime x, and this x prime x will be denoted by w. W now will be Wishart with these parameters here. It has a degrees of freedom, it has sigma, and it has delta, which is mu prime mu. So this notation here is read as W is a p-dimensional Wishart distribution with n degrees of freedom, covariance matrix sigma, and non-centrality parameter delta equal to mu prime mu. And note that both of sigma and delta here should be non-negative definite matrix. So if in particular your delta is equal to 0, then we say that W has a central Wishart distribution, and we only write this notation. So central and non-central if delta is not equal to 0. Okay, so to prove 17.6, we recall this theorem in chapter 3, which I've written here. So take note of the assumptions here. The y should be normally distributed with parameter mu and sigma squared I. This is for the univariate case. And then sigma here is just scalar. Then the yi's here are independent. Each of them are normally distributed. Then we can conclude this, that the square norm of y, this should be y prime y over sigma is chi-square distributed with this non-centrality parameter mu prime mu over sigma squared. So this is not a superscript. This is just mu prime mu. Okay. And in here it should be y prime y. So let's go over with some properties of a Wishart distribution. Okay, so the expected value for a Wishart distribution is equal to n sigma plus delta. So in the univariate case, you know that the expected value of a y, which is chi-square distributed central, is just equal to its degrees of freedom, no? N. But here, if we have a Wishart in general, if it is not non-central Wishart distribution, then the expected value of W is equal to n times sigma plus delta. So you see in the univariate case, we have a delta equal to 0, which is central, and a sigma, which is just equal to 1, or your sigma square is equal to 1 for the univariate case. So here, sigma is not necessarily equal to the identity matrix. But in the univariate case, if your sigma, which is equivalent to sigma square, is just 1, and it is a central, so that's why you have there, it is just equal to the degrees of freedom. But in general, this is the how you find the expected value of a Wishart random variable. So if P is 1 and your sigma is greater than 0 or is positive, so in general, it is chi-square, but you have a non-centrality parameter here, which is equal to delta over sigma squared. Again, delta here is mu prime mu. So delta here is mu prime mu. And if you do some transformation on W, say multiply it by a scalar, it is still a Wishart distribution with these parameters. So n, a sigma, and a delta. So, and another transformation here is AWA prime, and this is the parameters of the Wishart distribution. Again, we emphasize in the proof that when you try to prove, say Wishart is x prime x, and if you will have a AW here, so which is a W star, you have to find an x star prime and x star, no? X star prime, x star. So you have to find what is x star. So if this is the case, sa ganito ang ato ang x star din equal to, it is what? Anybody? It was what was our x star here?
XA prime, ma'am.
XA small a prime. So if that is x or x star, so to get a AW, so you will have XA star prime, then XA. Dinhi pa man ta, letter C. So this is wrong. So what's the correct? What was X?
A1/2 X.
So X star was
A
raised to the 1/2
X.
X. So this is X star, our AW here will be X star prime, X star prime, X star, which is A to the 1/2 X prime, A to the 1/2 X. So you will have x prime a to the 1/2 prime. Since a is just a constant, it's just equal to a raised to the 1/2. The prime is just a to the 1/2. And this is x prime ax, but a is a constant, so you will have x prime x. Okay, so that was our x star. And then if we are going to have AWA prime, so what was our x star prime? X star. So what was our x star here if we are going to have AWA prime? Mauto gitubag ni Sorongon ganina. It was AX prime, no? Mao man ni imong gihata ganina, Sorongon?
Si Ma'am Kali, ma'am.
Si Ma'am Kali yun. Okay. So if that is the case, so you will have what? A prime prime. A prime prime is just A, X prime, and then X A prime. So this is your AWA prime. Okay. So which is what we want. So this to note that that is how you generate your X star to make it X star prime X star. So in general, mao gyud ni siya. But you have to satisfy the assumptions of the X, no, or your X star, your new X star. Your new X star should satisfy the assumptions for it to be Wishart, which is duha ka buok. Unsa ganito? For it to be a Wishart, it must, ang katong imong bag-o na X star, ang imong bag-o na X star must satisfy this, no? Dapat normally distributed siya, pero mausab ng mga parameters din basta normally distributed siya, and each of them should be independent, no? And each of them is normally distributed before you can conclude that it follows a Wishart distribution. And the next result is when we have a partitions on your random matrix here, and you are going to get the marginal distribution of the diagonal entries, no? Yan ang mga diagonal niya. Okay? And then we tried to prove that. That is letter E. And we obtained the marginal distribution. So I just want to give this remark. This remark is not in the notes which I uploaded earlier. I just make this remark last night. So you can screenshot this or copy it. So this is about the marginal distribution. So theorem 1.3e tells us that the marginal distribution of any square submatrix of W. So if you recall, W was rewritten in this manner. So kini siya. Any square submatrix of W located at the diagonal of W, which is this one, so that the diagonal elements of the submatrix are diagonal elements of W, is also Wishart distributed. So this is what this theorem is telling you. I think I have one more remark here. This was about A prime. This theorem shows that the family of Wishart distribution is closed under certain linear transformation. So what you do, what you had is a W here, and you did some linear transformation by pre-multiplying it by A and post-multiplying W by A prime. So close, ibig sabihin, if it starts with a Wishart distribution, after that linear transformation, it still follows the Wishart distribution. So these are just the two remarks which I've added in the notes. So you can screenshot this or review it later in the recordings. Okay. And we were also doing some transformation of on X, which is normal, and it becomes Wishart even if we are talking about the projections. And since projections satisfies the idempotent properties, so in particular, if we have a matrix, square matrix n by n, which is idempotent, but on the condition that the rank of A is equal to K, where K follows the dimension of our subspace V, then this transformation here, x prime A, x is Wishart with these parameters, K, sigma, and you will have between mu prime mu the matrix A. And the next result is very important when we are trying to verify whether a certain linear transformation of your X are independent. That is, if that linear transformation, if you can isolate X there and multiply A prime B and it is equal to 0, then we can say that this transformation of your X here are independent. Another is this transformation here, AX and A prime BX are independent if these two conditions are satisfied. So this letter B is very useful when we are trying to prove that Y bar and sigma squared are independent because we can easily write Y bar as a function of an A, Y, and S squared as a function of Y prime, then B, Y. No? So you can always transform S squared. And also, if this linear transformation is done in your X, and you can show these three conditions here, then these two linear transformation on your X, puros na quadratic in form, no, are independent. So quadratic. So pag quadratic, chi-square and another chi-square distributed random variable, these are independent if these two are these three conditions are satisfied. So later, if you recall, how do we derive the F distribution or an F statistic? How do we derive an F statistic? Is actually what? It's found in chapter 1.
Ng dalawang chi-square, ma'am.
Okay, it's the ratio of 2 chi-square, no? So, and aside from that, those two chi-squares should be independent. So if you want to verify that those two transformations are independent, you can check this transformation. So if you can write it in this quadratic form and get the matrix A and B there, and check if those matrices are non-negative definite matrices, and if you multiply them, that is equal to 0, then you can conclude that So kung ang imuhang F is a ratio of this, no, in ani siyang forma, Bx, and there should be an assumption that they are independent. So you can use this theorem. Okay. So these three here are very useful in statistical, mathematical statistics, or in your inference also. I do not know if you have reached this part in your inference. So for the proof, which I skipped during the class, so you just look on this proof, which uses the concept of orthonormal basis matrix for V. So let's proceed now with these two results, which I have already also discussed. So if this is satisfied, then we know that the X has a rank of P, and that is almost surely, or that is with a probability equal to 1. And if you add, or if you append a matrix on X, say put an A there, so append mo ang matrix where A here is an element of an n by 1 vector there, not all 0, then if n is greater than P, then you are sure, almost sure, that the rank of this appended matrix will have a rank P plus 1. So kung X lang, P, no? But if you append it by this, and it satisfies these two conditions, then the rank of this new matrix there, this one, will have a rank of P plus 1, and you are sure of that. That is with probability 1. So for the proof, it uses the concepts of conditional distribution, linear dependence, because it talks about the rank, no? And you want it to have a probability 1. So linear dependence ang concept ani subspace spanned by X, no? And so on and so forth. So I will skip through that proof here. And then as a corollary on that, since we are talking about, you need that result to have this corollary, no? So since we are talking about a Wishart distributed random matrix here, so if these two are satisfied, n is greater than P and sigma is greater than 0, then we know that W will be invertible, and that is with probability 1. So invertibility of a matrix, or being a definite, positive definite matrix, assures us of an inverse of that matrix. There is a short proof on that uses theorem 1.8a in the book, so that W will be invertible, and the assurance that it is invertible is with probability 1. So note, so if sigma is positive definite and n is greater than or equal to P, then W is called the non-singular Wishart distribution. If we ignore the null set on which W is not invertible, and we can assume that W is positive definite. But if either of these two conditions are not satisfied, that is n is balian, no? N is less than P, or sigma is not positive definite, then the central Wishart distribution is called a pseudo Wishart distribution. Here it is referred to as singular distribution. So it's a term versus non-singular Wishart. So Pag masatisfy niya ang two conditions, then non-singular. Pag dili niya i-satisfy either one, no? Either one, then it is a pseudo-Wishart or it is a singular Wishart distribution. Now, for this important lemma, it starts with a W, which is Wishart with these conditions here, and we partition it in this manner. It tells you the different distribution of T, where T is your entry W22. U is the product of W22 inverse W21. And V is this component here, W11 minus W12, W22 inverse, W21. This important theorem tells you the distribution of your W22, the distribution of U conditioned on T, and the distribution of V conditioned on U and T. So this is Wishart, this is normal, and this is Wishart. Now, the use of this important lemma, in particular when Q is equal to 1, which this is the flow of the proof here. This is quite long, but look into it and understand it. The application of that important theorem, one application, is when Q is equal to 1, and that will be your coordinatized version of the linear model. So we discussed this. This is this here is familiar to you when we tried to find the conditional distribution of y given x, no, in terms of beta. So you have these results. So this is just deriving what will be the conditional distributions of V given X, which is Wishart, and U given X, which is normal, and katong W22 ganina, which is Wishart. Conditions. Conditional ra iyang gikuha. Okay, so we start now here. This is where we end up. Section 1.3 is actually your 17.3. Unless you have any questions. Do you have questions?
Wala ra, ma'am.
Wala po.
Okay. So let X and W be independent. So for it to have an Hatteling's t-square, please note of the assumptions here. You have to check that X and W are independent. So unsa may gamiton ana to check that? Mao ni ang usefulness aning tulo. Unsa to na theorem? Kini. Now this is theorem 17.7, no? Verification if X and Y, W there are independent. Okay, so let X and W be independent. X is normally distributed. W is Wishart. These two are very important assumptions for a W inverse to exist, no? Because if these two assumptions here are satisfied, then we are sure that W is invertible with probability 1. Now we define a new statistic or a new transformation on x prime x, W inverse, and x. So this is a transformation on your x, which is normal. So quadratic ang x, mangi na kay gi-multiply na W inverse and pre-multiplied by this constant here, which is a function of the dimensions of your x and W and degrees of freedom. So if we define a new f value here, or an f statistic, which is a quadratic in x prime x is quadratic, and then na kay pre-multiplied by a Wishart distributed random matrix where the inverse is existing. So we define this f is n minus p plus 1 over p, then x prime W inverse x. Hatteling's t squared will be in terms of f. The Hatteling's t squared is equal to np over n minus p plus 1 times f. Or that is equal to t squared is equal to n x prime W inverse x. So this is np times n minus p plus 1. Then your f is n minus p plus 1 over p times x prime W inverse x. So this is cancelled. So you have n, then x prime W inverse x. No? So if p is equal to 1, what will happen here? This will be n times p, 1, n minus 1 plus 1. This is n over n. And that is just equal to f. And that f will be equal to this one. Nood ba na? So x squared is x prime x. Kay p is equal to 1 man. So may mo na siyang x prime x over here W over n. No? So may mo na siyang n rag W inverse x prime x, or pwede nimong isulat as n x prime W inverse x in general, no? But p is 1, so muna pwede na nimo i-swapping lang sila because p is 1. Are you with me? So this form here can just be written in this manner. Kaya ang imuhang x prime x, kung univariate na siya, mao man na ang x square. Are you with me? And then kini nasa denominator, no? And this is the familiar t, non-central t, no? The square of a random variable which is non-central. This non-central t, that's why it is related with t square. And this is actually an f with a p equal to 1 degrees of freedom. So ang special case sa f when p is equal to 1 becomes a non-central t distribution. In general, so ibig sabihin, ang non-central t distribution, ang general case ana, ang generalized version where p is not equal, is greater than 1 will be an f. Okay, so lemma 17.10 is quite a long lemma. So let's have a break first, 10 to 15 minutes break. So let's,
Yes, ma'am.
okay, so let's continue now. Lemma 17.10. So let's look at this assumption. We have a W, which is Wishart distributed, and this assumption is again important for a W inverse to exist. And we know that sigma is also positive definite, which makes sigma inverse exist, so that these two terms here will be defined. So let A be P by 1 vector. A, not all A is equal to 0. Then the ratio between A prime sigma inverse A. So this is just, if you look at the dimension of this is 1 by P, P by P, P by 1. So this is just a 1 by 1 entry here. The same thing here, no? So that's why it's central chi-square with degrees of freedom n minus p plus 1. So n will be for your number of cases, and then minus p. Actually, it's n minus p minus 1, no? So p minus 1. That is your degrees of freedom, n minus p minus 1. So because there are two parameters here, so you have to correct it minus 1. So that's why it's n minus p plus 1. So the ratio of these two will be chi-square distributed. So if you recall in chapter 1, when do we have a chi-square distribution? Chi-square distribution is you start with a normal random variable, and then quadratic form. So that is chi-square. And then T is a ratio of normal over chi. That is your T. And F will be a ratio of chi over chi. So normal. But this is just scalar. So according to this lemma, it is chi. So to show that, this is by the fundamental principle PMI, principle mathematical induction. So you start with that it is true for A equal to A0, where A0 here is a vector of 1, 0, 0, 0. No, this is A0, A sub 0. So if this vector here, because not all are zeros, so kung naay isa 1 diha. So what will happen here if kinira ang mabilin diha? So what will happen? Ang kinesia will no longer be, it's just a 1 by 1 entry there. So that's why W11 and sigma 11 will just be a 1 by 1 entry, and the rest will have this dimension. So again, these assumptions will have as W to be invertible. Okay, so let's find out what is W11.2, which is this component here. So that is W11 minus W12, W22 inverse, W21. This is necessary for finding the inverse of W. And let sigma 1.2 be this linear transformation on your sigma components. So matrix algebra tells you that if you want to find the inverse of W, if you have this form, then the inverse will be equal to this form. So it's the inverse of W here. We'll have this entry. So the inverse of this there. And then this entry. This. And then, asang kamaan eh? This entry. And this entry here. So that is a matrix algebra, or you can check appendix A in Arnold. So that is the components of getting the inverse of a matrix. So from this form, the inverse of a matrix will have these following entries. This one, which is the inverse of that. This one, and then this one until here, and this one. So those are the components of the inverse. So that if we look at the numerator here, denominator rather, this one. If we get A prime W inverse A, where A here is particularly equal to A0, no? Then this will be equal to W11 dot inverse. Kini siya, the inverse of this, no? Kaya kung imo ni i-multiply by A prime 1, 1 0 0 0 dot man kini A prime, no, man 1 0 0 0 1. Kung kuha nimo ang entry ani, multiply ni paingon dinhi, kini ray mabilin kay 0 na ng uban. And then dinhi na side, ma 0 na siya. Man i-multiply ani, kini ra na mabilin. So it tells you, are you following? So i-multiply nimo og 1 0 0 0 0 dinhi, man kini 1 0 0 0 0. If you look at the entries here, unsa may mabilin kay nira, no? So that's why it tells you na A O prime W inverse AO is just W inverse 11.2, which is the inverse of this. The inverse of this. Are you with me?
Yes, ma'am.
Okay.
Yes, ma'am.
And then similarly, if we consider this one, and then you prime multiply it by A0 prime sigma inverse A0, what remains is the inverse of this. Like, maumangyapon na entry diha if you get the inverse of sigma, no? So the inverse of this. Kuhaon mo ang inverse ani. So that is what is referred there as similarly. Okay. So now we get the ratio of this, which is equal to this. Since this is just inverse, you can write it in this manner. But how we define W11.2 will be equal to that, and W11.2 will be equal to that. So by lemma, the important lemma, wherein we have V to be defined as W11 minus W12, W22 inverse W21, which is this. So this is actually your V. And then if you condition it in X, according to that important lemma, it becomes Wishart. So that is by theorem 1.6b in our notes, but in our note, that's 17.6b. The important lemma na siya. And then if we condition it, Wishart man, 1 raman siya, kay 1 by 1 man eh, sa ibabaw. This is just a 1 by 1. So when particularly equal to 1, it becomes chi-square. So central. So V condition of X will be equal to sigma 1, 2 times chi-square distribution. So ibig sabihin, if you put this down here, so chi-square na lang siya. Because V conditioned on X will be your W11.2. Okay? So what we obtained is that this one, we know that for A equal to A sub O, that is just your W11.2 inverse. And W11.2 is given by this. And this one is given by that. And if you get the ratio of that, so W11, so finish siya. Substitute ni mo ani, no? A sub O man ni siya. A sub O. Kini. So if you look at the theorem, sigma ang ibabaw, no? Sigma ang ibabaw. Ang sigma ang ibabaw can be written as in this manner. Okay? Kini. So, which is equivalent to that. And that is chi-square distributed. So this lemma is true when your A in particular is vector, no? So now we'll have to do it in the general case. So tinuod siya when A is AO, and then general case when A is equal to a matrix A times AO. So nakaka i-pre-multiply ana. So general na, whatever is your A there. So this is by induction. So let A be P by 1 vector, not all 0. The entries in A, not all 0. And then you have an A, which is an invertible matrix. So first column is A. Then A is equal to A times A sub O. So ang first column is A. Man kini siya is just an entry of 1, 0, 0, 0. So ang mugawas ani, ang whatever is this, ang mugawas ani, si A ra na siya, no? Kaya ang iyang component makuha diha, ang entry ra sa A. Kaya ang how we define A, the first column should be A. So i-pre-multiply nimo og A sub 0. So ang iyang makuha na entry lang is A regardless ang say sulod ana, basta ang first column niya is A. Okay? So, W Wishart, if you do some transformation on a Wishart, it's still Wishart. Are you with me? Do you understand? Okay, W is Wishart. Do a transformation on Wishart by matrix A there. It's still Wishart. So, if it is still Wishart, if we have kini na karon ang imuhang sulod, no? This form. Sa ganitong assumption ani, dapat ang W sa ilalom is Wishart. W inverse. So kini na transformation now. Wishart man eh. So this is still chi-square distributed. And then if you try to simplify this, why is this equal to this second? So you have A inverse sigma, A inverse prime. Get the inverse. It's just equal to A prime inverse A. Maura man eh. So why is this two equal? So kung imong tan-aw na closely, muragi suod din, no? Can we do that? Why can we do that? Imong tan-aw na result ba kana from here to here. Murag nahitabuan na kana siya gi so diha kay negative times negative na imo na lang siyang positive man pero mura siya nabataan na result mura siya nahitabuan na B inverse A inverse kay kana siya ang kini siya nimo siyang A transpose dito man nimo siyang sigma inverse and then kini na imong A. Can we do that? Do we have a result na inana na siya? Or what are the assumptions na pwede na siya mag-inana? Wala siya ginani ang naitabo. Rakag na ay A, B, C. Prime. No? Man inverse. So naitabo mura siya C prime inverse, B inverse, A inverse. Pero ang atong C prime din kay ano man prime mo nang A na lang siya. Kini mahimong mura siya C prime inverse, B inverse man A inverse. A prime. Ang original nato prime. But can we do this? Do you have a result something like that? Siya A inverse sigma A inverse prime. Common imong pag prime nimo na imo siyang A inverse prime inverse sigma inverse A inverse. So may mo siyang A prime sigma inverse A. Okay? Can we do that? Do we have a result? Or Pwede ni siya? Nani siya na ano? Na result? Kaya maogi na nahitabo. But, and then from here, this one is just A. This one is just A prime. Because that is how we define that. So my question is, can we do this? Kinina ano? Kinina inverse property. Do we have inverse property for that? Kaya maugin na naitabo din eh. Siya A, B, C. Sa prime, tinuod na. But is that true for inverse? A, B, C prime. Marama siya C prime, B prime, A prime. But can we do that in inverse? Say A, B. A, B, C inverse. Is this true? Do you have results for that? Or do I have assumptions for that before we can do that? What are properties of inverses?
Inverse of our product, ma'am.
Mura siya inani. Kini. This one. Do you have results for this? Is that properties of inverse of matrices? Because that is what happened there. And then A inverse is just A. Is that correct? So I want you to check this properties of inverses, huh? Because if this is assured, then we can have this. Hindi man mo maningog, so i-research na ninyo. Okay, because that is, if that is true, then by induction, proof by induction, we are done, no? Okay, let's proceed. Theorem 17.11. Let X and W be independent. Your X is normal, your W is Wishart. These conditions assured us of the inverse of W. Then this F, which we defined earlier to be N minus P plus 1 over P, X prime W inverse X is F distributed. So again, when do you get an F distribution? So you get an F distribution, chapter 1 of Arnold. You get an F distribution if non-central F distribution with M and N degrees of freedom. If F, these are the conditions. So for an F, X should be chi-square, M central, a non-central, you have Y chi-square and central. You get a ratio of X divided by M over Y divided by N, or that is X over Y times N over M. So this one is chi-square, non-central, over a central. So ibig sabihin, for this to be chi-square, you look at the ratio, no? So how do we write this as a ratio? Asa gani ning ano? Asa gani ning kang kinsa gani ning n minus p minus 1 kang Wishart. And then si P para kang sigma. So you have to rewrite this as a ratio of non-central chi over central chi. So to prove this, so dapat masulat ni nato as kinitanan. Are you with me? Dapat ano ni siya, chi na non-central man chi na central, no? Ratio. So to do that, let's start with this notation. Let U be x prime o x prime x man so chi gini siya kay quadratic man sigma inverse din and V to be x prime sigma inverse x over x prime W inverse x. X is a vector. So, by the important lemma, the conditional distribution of V given X. So, X is normal, ha? V given X is central chi-square. So, kung central chi-square ni, okay, an additional also sa FDI kay X over Y times N over M. Aside sa si X, chi-square, non-central, man si Y, chi-square, central. Another additional assumption is that X and Y should be independent. No? Para kining F mahimong F statistic or F distributed. Okay. So kay central man so naani siya sa denominator. So V given X, central chi independent of X and therefore also of U. So because U, a function of X man independent of X man siya, so put siya dependent sa X. So if this is independent of X, then the marginal distribution of V is just the same, no? So either you get it conditionally or not. Since it is independent of X, then it is chi-square. So consider X. So ang kining V, imo na nangunaw-naon na si V, kining denominator, karon kung imo ni i-denominator, kini si V, chi-square central na siya. Okay? So ang ato ang tan-awon is the non-chi-square central. So kini siya para mahimo ni siyang kada man kung kini denominator unsa may projection ninyo si F sagdi lang ni siya ha star. So kung kini na si V sa ubos star na man si V kay x prime inverse x over x prime inverse x. So unsa may dapat naa sa numerator para mo gawas ni? Sa projection ninyo na nasa numerator. Wala.
X prime sigma.
So dapat na si x prime sigma inverse x kay makancel man mo ato na dayon ni sa ibabaw. Are you with me? No? Mao na imong aim. So paano na to ang distribution ni x prime sigma inverse x? So unsa may distribution ni x prime sigma inverse x. So ibig sabihin kini si u. Paano di mo ang distribution ni u? So, unsay distribution ni U? Distribution ni U is, kay quadratic man is chi-square with this centrality parameter. And you can see that theorem 3.10a, no? Ang inyong makita dito katong x prime is sigma a x. Anong theorem 3.10. Theorem 3.10. A tells you that kung si y daw is normal, mu sigma, then y prime sigma inverse y is chi-square and mu prime sigma inverse mu. Okay? So, using that theorem, you can have this result. So, tinuod ni siya by theorem 3.10. So may tabo, it's u over v, no? Where u is chi-square non-central, v is chi-square central. So the ratio of u over v, chi is non-central over chi central, and of course si v mo ni iyahang degrees of freedom n minus p minus 1. Okay, unsa man na si v? Function of w, no? Na si w diha. And sigma, so si sigma n, then minus si w, p minus 1. And then cu, function of sigma lang, so p. So actually, what is happening here is this is u over p and v over n minus p plus 1. But u is chi-square non-central, v is chi-square central. Ratio of two independent chi-square will be f distributed. And if you try to substitute for the values of u, which is x prime inverse sigma inverse x, v to be x prime sigma inverse x over x prime w inverse x, this will give you x prime w inverse x. Okay, so that's it for the F statistic, and recall that you can write the Hoteling's T square in terms of F. Okay, so this is the probability density function of your Wishart distribution. So if you look at this in terms of trace and in terms of gamma, this is in general the general case of a gamma distribution. So kung tanaw ninyo unsay gamma, unsay probability density function sa gamma distributed sa gamma distribution, more or less similar ana, no? And then special case is the chi-square distribution. So tanawa gani ninyo unsay probability density function sa gamma distribution, mas general ni siya ba na ay i-specify na values that it becomes a gamma distribution. And naapod kay specify na value din that it becomes a chi-square distribution. So special case ang gamma and chi-square of the Wishart distribution function. So the proof is by induction. We will not deal with it because it uses the Jacobian matrix of determinants, and this is how it is done. And as a corollary, special case, this is the density of your Wishart distribution. If in particular, in ani lang ang distribution, no? Dili katong kompleto. N sigma lang. Kini manggod, kompleto ni siya, which is Ni. A particular case ni Ni. Katong corollary is N sigma na. Ni man kini N sigma. Okay? So mas general ni siya. This is the general probability density function. So we will not deal with the proof there. Okay? And let's have some other results. Okay, first result. Theorem 17.13. Let X be normally distributed, T be M by R matrix, then the trace of TR is T prime R. T prime X will be R by M. X is M by R. So this is an R by R square matrix. So it has a trace. Get the trace of this, trace of an R by R matrix. So it becomes singleton or scalar, 1 by 1. Actually, 1 by 1, dili nila gusto na i-equal na siya, calling it scalar. No? 1 by 1 is not necessarily equal to scalar. But actually, gusto lang nila i-refer ang scalar kung constant din siya. This is derived from a matrix where components inside the matrix can be random variables. So, mo nang dili nila gina-equate. So, the trace of T prime X will be normal because it starts normal and any transformation on a normal is still normal. So the mean vector will be the trace of T prime mu, and the covariance matrix is the trace of T prime psi sigma. So before I will discuss B, let's look at the proof of A. So tawag niya scalar, but let us change this to be a 1 by 1. No? Actually, constant man gina siya. Anyway. So let U be the trace of T prime X. We are trying to look at the distribution of the trace of T prime X. So we have to look at the moment generating function of U, or the trace of T prime X, because moment generating function is distinct. So kung kana ang iyang moment generating function, man related na siya to a distribution. Okay? Note that X here is what? X here is normal by assumption. Normal, no? Okay, normal siya. So the moment generating of U, by definition, is the expected value of the exponential of TU, or that is equal to the expected value of the exponential of T times U is the trace of T prime X. And then by property of a trace, pwede ra na nimo isulod sa sulod. So you have this. And then by property again of a trace, that is the trace of AB is just equal to the trace of BA. So here the grouping will be ano, ang igagamit kay unsay gigamit din not this. Silang duha. AB equal to the trace of BA, and also the trace of A prime is equal to the trace of A. So ang primero gibuhat, the trace of primes. So T prime X prime will be X prime T prime. And then, una. T, unsa ni siya? Mo follow ni siya sa dimension sa unsa? So naa kay ano? T prime X. Kuhanin mo ang prime ani, T prime X prime. According to this, kini man daw gigamit. So this is, by definition, is X prime T, kay T prime prime, man T prime, no? Correct?
Yes, ma'am.
Yes, ma'am.
And then, anong name mo man na siyang T prime T. Ano man ni siya, na pwede gibalhin din uman ang T prime which is T. So kung kuhaon ako ang prime sa T prime, T siya. That's the reason. Unsa nang T? Unsay dimension sa T? Kano sara gani ni mahitabo na ang T prime is just T?
Scalar.
Scalar, ma'am.
Oh. So nganong scalar si T? Mao man ni
Ano siya
nahitabo.
sa
Mao man ni nahitabo kay T prime is T man pwede kay tungod kay scalar siya, pwede siya ibalhin before sa T. So, tinuod ba na scalar si T? Tinuod ba na scalar si T?
Yes, ma'am.
Why?
Okay, mag-follow siya sa dimension sa U, which is 1 by
Okay.
1.
Okay, very good. So, mao na pwede na siya naon, no? Okay, so let's proceed. Isa to nito bag,
Inyola, ma'am.
Okay, very good. Next. Tinitabo. Di ba ang definition sa moment generating kay expected of the exponential of x prime t, no? So, ibig sabihin, kung maitsura na nimo diha, mao na ang moment generating function sa x at t. So, ang itsura ni, mao ning moment generating function sa x at t, capital T. Correct?
Yes, ma'am.
Yes, ma'am.
Okay, so kana. Pero ang atong x is normal. So kung normal si x, sa ganitong moment generating sa normal, di ba? Exponential of mu prime t plus 1/2 the trace. Multivariate xt. Moment generating function sa normal, exponential of the trace of mu prime t plus 1/2 trace of t prime una, psi t sigma, unsa una, t prime? Dinhi ang t prime. Okay, dinhi ang t prime, no? So, trace of mu prime t and then 1/2 trace of t prime sigma t sigma. Okay? Which is tungod kay t scalar, pwede ni ipagawas kining t dinhi og t kana ang mabilin. So kung inani ang forma, wala siya trace of t man kana ang nasa tunga man t. Kay scalar na lang siya. Kung univariate na lang siya, di ba, may mo na siyang 1/2 of t squared, no? T squared sigma. Anyway, mao ni siya. So kana na forma karon is the moment generating function kay si mu prime t unsay dimension? Okay, ni ang mu as a whole, the trace, and then mao ni si sigma na term, no? Because t is scalar. And then we are done, no? We have shown that the distribution of the trace of t prime 3 with these conditions here is still normal. Okay, next. Say sunod, letter B. Letter B has this assumption x and then positive definite si psi o si sigma and then quadratic transformation with psi and sigma, chi-square central because you subtract it from mu. And if it is not subtracted from mu, then it becomes a chi-square non-central. Okay, so that's the next result. Let me see if we have a proof here. Yes, we have a proof, but this is actually similar to your theorem 3.10, wherein you have a y normal n mu sigma greater than 0, univariate case. The transformation y prime sigma inverse y is chi-square and mu prime sigma inverse mu. And the transformation y minus mu sigma inverse y minus mu is chi-square central. So we will use this result except that we add a trace on it, no? So we look for the trace of y prime y. So by definition, man chi-square sigma, you have y, which is normal, independent, then the trace of y prime y is chi-square. So actually, that will be your non-centrality parameter, the trace of mu prime mu. So if we define our z, kaya ang atong buhaton ani, unsa ganito, ato man ang i-transform og z prime z. Kanus unsaon mi nato mag-itsura ni siya og ani. Na z prime z dapat, no? Z prime z. So, mag-define tayo nani. Kana. Or equivalently, i-distribute nato ning kana paingon deha og kana mao ni siya. Man kini siya paingon dinhi mao ni siya. Okay? And then you have to verify that this form here is normal. Okay, mao man na assumption sa imong kay dapat normal siya. You use theorem 17.2 to do that. So that is normal with these parameters. This is the mean vector, this is the psi, and this is the sigma. You have three components of your parameters. So if you get the primes of a symmetric matrix, is just the same, no? Symmetric man guna sila. So it's just the same. So that this also is just equal to the identity matrix. So in summary, if we summarize this, that one and that one is just the identity matrix. So your Z is 0 II. Okay? This is 0 because this is the same as this term. So that is 0. So paunday nimo ang trace na Z prime Z. Actually, mao na imong gusto. Okay, mao man ang imong target, di ba? So nangita ta og Z, pareha ni siya katong sa Wishart na concept ha. Nangita ta og X star such that pag X stars prime X star nato mugawas ni siya. Okay? So get the trace of that and using the result theorem 3.10, the trace punan lang ni mag-trace, the trace of Z prime 3 Z will be chi-square distributed. So the same thing, if we define our Z to be this, so mao ni ang diferensya lang, kini siya mao ni atong Z for this form. For this form, mao ni atong Z. Okay? Mangkwaon ang trace sa Z prime Z. For this form, mao ni atong Z. Are you with me?
Yes, ma'am.
Yes,
Okay.
ma'am.
Ang target Z prime Z. Pero i-check sa ninyo na kana inyo ang gipili na Z, normal, no? Mo-satisfy normal. And then, kuhaon ninyo ang Z prime Z. Pagkuha nimo sa trace, chi-square siya. Okay? Okay. So, let's again have a break to continue with theorem 17.4. Sas pa ni? I want to, let's see if we can finish it today so that you can study tomorrow and Thursday for Friday's exam. Else, I will finish this tomorrow, but still the exam will be Friday. Okay? Uban ani dili naman ako ni approve. Ato lang i-discuss ang result. So, what do you want? We'll have a break ha, 10 minutes. Stop recording, Sorongon. So we will start. So let's take up theorem 17.14. And we look here some properties of some more properties of the Wishart distribution. Here, Wishart, W is Wishart distributed. And if we do some transformation on W, that is, we get the trace of a Wishart random matrix pre-multiplied by the inverse of sigma. You will still have a chi-square distribution. This is NP because the dimension of this matrix will be n by p. Why is this n? This should have the degrees of freedom is NP. And this is a non-central chi-square with non-centrality parameter trace of sigma inverse sigma. So W is P by 1. Matrix, what is this? N times P. Let me check the book. Chapter 17. This is 17.14 P NP git siya. N times P. Anyway, let's look at the dimensions in the proof. Wishart meaning W is obtained from an X by X matrix X n by P utilizing the previous theorem 17.13b. If you have an X n by R, so m times R good, no? Ang chi-square. So this is correct. Then times R. The degrees of freedom is n times R. You utilize that, then that is chi-square non-central with trace mu prime psi. Psi is I. Psi inverse of I is still I mu. And then sigma inverse. Okay, this is correct by this theorem. This is actually 17.13b, the second part. And if you scrutinize this term here, since this is just I, it will simplify to this. And the non-centrality parameter will be equal to this. So the proof is straightforward. This is using theorem 17.13b. Okay. Next, we have some additional properties of the chi-square Wishart distribution. We still assume that W is Wishart distributed with sigma positive definite. So we are assured of the inverse of sigma. Then the moment generating function for a Wishart distribution. Again, a moment generating function is distinct for a particular random variable. So if you see a moment generating function that looks like this, then that is for Wishart. Can anybody know the moment generating function for a chi? Let's see if somewhat it's similar. This is found in your book. Else, let me have a Google. So let us see the moment generating function for chi square. So it is in terms of gamma.
Hey guys, Alexander here, back with
Moment generating function. Chi 1 less than 1. Okay, so if you look at the moment generating for a chi square, the univariate case, similar ang itsura, ana. You have the moment generating function of a chi, x is chi square n is tanawa 1 minus 2t raised to the negative n over 2. So with some conditions on your t, tanawa, no? So it's just more or less similar. I for 1, then 2, and then nalang kay additional variability among, because this is just univariate case. So this is assumed that sigma square here is just equal to 1. So we see that Wishart is really the generalized version of your chi. And it has similarities with your gamma distribution for some special values of your parameters. Next, if n is greater than or equal to p, then the ratio of the norm of, or this is not more or less mura siya determinant or absolute value in simple terms, no? Determinant of W over the determinant of sigma. Actually, when we are talking about matrices, ang kanang murag absolute value will be the determinant. We'll have the same distribution as U, the product of U, so joint density function of U, where each of the UIs there are independent. And then we have another expectation of the determinant, no? So kanina katong expectation sa W, which is n sigma plus delta man to, no? Tama? Okay. This is the expected value of the determinant of W, which is equal to this. And the expected value of its inverse is equal to the inverse of its expected value. So you have those formulas there. So what's the difference between this and this? So this is the expected value of W inverse, but this is the expected value of the determinant of W, the inverse, no? The determinant of W. Then we have expected value of the trace of W is equal to n times the trace of W. And then if this condition holds, you have that. So these are just properties, some more properties of your Wishart distribution. If we can assume that W1 and W2 are independent and each of the Wi there are as a Wishart distribution, then if we do a linear transformation, the sum of two independent Wishart, will still be Wishart with degrees of freedom N1 plus N2 and variance sigma. So it means here it is closed under linear transformation of addition, no? So if you expand that, in the univariate case, if we have x to be chi-square distributed n, the sum of chi-squares is still chi-square, no? But the degrees of freedom will be the summation of ni's. And then the next result is we do some transformation on the inverse of W. It's still Wishart. So if we have a W which is Wishart, and then we do certain transformation on it, linear transformation, with respect to the inverse of W, which has a Wishart distribution, and that get the inverse of that, it's still Wishart. So you have some proof here that you can look into. The first is letter A. So letter A talks about the moment generating of a Wishart distribution. To prove that, you have to know these two results. If A is a matrix and B is also a matrix, then identity plus AB is just equal, the identity matrix n by n is just equal to, plus AB is just equal to the identity matrix m by m BA. So AB is n by m, B is m by n. So that's why this is n by n. B is m by n, and this is n by m. So this is m by m, no? So because the dimension of AB may not be equal to the dimension of BA unless both of them have the same dimension. So according to this result, the determinant of this is just equal to the determinant of that. You are going to use that when we try to prove A. And a symmetric matrix A is orthogonal, similar to a diagonal matrix D. That is, you can write A as a function of D pre-multiplied by gamma and post-multiplied by gamma prime, where gamma is an orthogonal matrix. So you can always find an orthogonal matrix such that A will be equal to D, but D will be pre-multiplied by that orthogonal matrix and post-multiplied by the inverse of it. No, inverse, the prime of it. So to get the moment generating function of W, you note that W is Wishart, and by definition, that is how we get the random variable which will be Wishart distributed, with this assumption that X is normal and each of them are independent and normally distributed. So if we have a standard normal Z and pre-multiply it by C, where C here is a function of your sigma, no? Sigma is CC prime, then CZ is also normally distributed. So the difference is that I will be changed to sigma. So this implies that more or less our transformation CZ will have the same distribution as our X. Our X is normally distributed. And then we introduce an orthogonal matrix D such that this orthogonal matrix, when pre-multiplied by its transpose or post-multiplied by its transpose, it is equal to the identity matrix. That is property of an orthogonal matrix. So that T prime Z is also normally distributed, but this is I. So we see that C Z or Z, not CZ, Z with this distribution here will have more or less similar distribution as T prime Z. So since T is symmetric, it follows that C prime T is also symmetric. And if we use our result earlier, this one, we can always find an orthogonal matrix to make it equal. So there exists an orthogonal matrix such that we can write this as a function of D. So this is our whole matrix. No? And then if you follow through this definition of your moment generating function, property of a trace, property of exponential, which is the exponential of the sum is just the product, and use the assumption that they are independent. So if they are independent, then you can write the expectation of xyz to be equal to the expectation of x times the expectation of y times the expectation of z. No? So this is what happened here. And then you apply the property of the trace within. So what happened here? This is just the trace of AB is equal to the trace of BA. And then the product of identically distributed random variables can just be equal to raised to n, no? Instead of getting the product that is A times B times C. So if these are IID or identically distributed, so you can have A to be equal to B equal to C. So what you will have is just A raised to the n. So this is what happening here. And if we scrutinize this term, this is a univariate. This is supposed to be with a prime. This is a univariate term here. So that A x prime prime is just equal to x. So this xi here can be written as x prime prime. And then since we have shown that the following has more or less the same distribution, so you can substitute the x's here by CZ. So they are equivalent in distribution, so you can substitute it there. And you have also this result that is equal to C prime TC. So substitute it here. And then do some equivalent expressions on this. This is retained. And use again the result that they have this, they are equal in distribution. So you have that. So if we go back on how we define Z, which is standard normal, and you have a D of this form, a D will always exist, no? If we pre-multiply it by an orthogonal matrix and post-multiply it by its transpose. And then you look what is the form of this Z prime DZ, which is equal to this after matrix multiplication. And you know that each of Z is standard normal, and then you square that becomes chi, correct? And it is chi, and y is also chi. So we have that this moment generating function for a chi-square distribution, which I've shown earlier. Like instead of n, that will be r. So it follows that if y is chi-square, or any random variable which is chi-square will have this moment generating function. 1 raman na siya. So that if we again apply the moment generating of W, which is this time we use Z prime DZ instead of the original form, which is kini natong gamiton, instead of the original form, which is atong in terms of X pa, since they just have the same distribution. And then you can follow through this by these definitions here. So mao na niyang moment generating function, each chi, and then you get the product. That is how we arrive at an identity matrix I minus 2D raised to the n minus 2, negative n over 2. So since I minus 2D is a diagonal matrix whose diagonal elements are these, and the determinant of the diagonal matrix is equal to the product of its diagonal, thus the moment generating function of W will be equal to this. So you have your CC prime here to be denoted by sigma. And that is how you prove the moment generating function of a Wishart. So daghan concepts na gamiton to arrive at that. And then this is the expected value of the ratio. And then you use the result in 17.15b and the concept that they have similar distribution, linear transformation or linear operator, and independence will have this. But the expected value of UI, since it is chi-square, will be equal to its corresponding degrees of freedom. So that you will have that. And then this uses density function. So just look into it. Hindi na ko mo discuss ana. I will just discuss okay, just be familiar of the values directly, no? And this is just using, you play around with the trace and linear transformation or linear operator. Ako mo discuss ana. Anyway, just familiar with the results, and this will have many concepts to apply so that before you can prove this one, no, to show this. So I think ana lang. So just take note of the proofs which I discuss and emphasize. So because more or less that will be the one that I will ask during your exam, no? Especially the concepts which I emphasize that you should be familiar with. So that's it. So I think chapter 17 is done.